I'm Timothy Precella, and today we're going to discuss synthetic division and zeros of polynomial functions. And the first thing I want to do, don't write this down. Do y'all remember polynomial long division? Here's an example. You had your little division symbol, and y'all remember doing that in your previous math classes? If you don't, it's okay.
Okay, we're not going to do this today.
Okay.
We're going to do a shortcut.
Yeah, we have a shortcut method that takes the place of this long polynomial division process. It only works when the divisor is in the form variable, plus or minus a number. But you'd be surprised how often that's all you need. I mean, your divisor really is in that form, so it's not going to be a hardship that we can only use this shortcut method when the divisor is in the form variable plus or minus a number. And maybe we better discuss, let's remind you all of the terminology before we go any further. Move that down.
Move it down?
Oh yeah, okay, you do. That's good.
If you're writing division with this symbol here, the two dots in the horizontal bar, then the dividend is the first thing, divided by divisor. And do y'all remember what the answer?
The name of what do you call the answer of a division problem? Starts with a key.
Yeah, quotient.
Yeah, that's right.
So you might see division written like that.
Or it could be written as a fraction.
Or I want to do this first.
Oh, okay.
Because dividend goes under the division symbol. Divisor out here. Quotient is up here. This is some terminology you may not have heard. And sometimes stuff doesn't divide in evenly. And there's something left over. Do y'all remember what that's called?
What's this? The remainder.
Yeah.
That's right. Okay.
So we could write division with this little two dot symbol. It could be written with we used to call it a long division bar.
I prefer the fraction bar.
Dividend, if it's written with a fraction bar, then dividend is on top, divisor on the bottom.
Equals quotient.
Yeah, equals quotient.
You know something? Write it dividend over divisor equals quotient, and then say plus. Show what they do with the remainder.
Oh, okay. Dividend divided by divisor equals, the way you state your answer for a division problem, sometimes it'll just say quotient and then say remainder equals. You might see that if there's a remainder other than 0. But other times, it might be written like this, sort of like a mixed number. Quotient plus remainder over divisor. That's what you're doing when you write 5 over 2 as 2.5. Okay? Or 7 over 2, if you write it as 3 1/2, 7 divided by 2 is 3. With the remainder of 1. So 7 divided by 2 is 3 1/2. Quotient plus the remainder over divisor.
You know what I think would be fun, Tony?
What?
I think I want to take this long division problem and do it using synthetic division. So you can write the problem down, and I'll then...
Okay. But I want to go ahead and make a statement. We can use synthetic division.
Okay,
this is the new stuff, the stuff you need to know how to do. When the divisor is in the form x minus some number k.
I say x plus or minus because it can be a plus also, as long as it's just a variable and then plus or minus a number.
Well, I was going to say x minus k and then x plus or minus number. Because, k is clearly defined. Okay? And that's not a good red there. Okay, so we're not going to write out a sequence of steps on how to do synthetic division. And once you see it, you get students get the hang of it pretty quickly. But writing out, I've often thought, how would I write these steps out?
And you've done it before.
And I have.
With disastrous results. It's just easier to...
The pattern's easy.
Mm-hmm. The pattern is easy to see, but writing out what you're doing, that's another thing.
This one might be better.
Yeah, yes. Okay, so what we're going to do, remember that problem that we had just now? Here it is. Let's do, instead of this long division process, let's do it using synthetic division. Let's do it.
And you missed us discuss how to do that long division process, so you're just going to be lost all class.
We didn't discuss this.
We said we're not doing this long division.
We're not doing this.
But you remember doing some messy division sometime? It used to be taught after foiling. When you were in Algebra 1, you foiled, and the foiling you do over and over throughout algebra, and then you do this division, which you do it and you never do it again.
Mm-hmm.
Okay? So if you've forgotten it, okay. But we want to demonstrate something called synthetic division, which is a lot shorter.
Okay, so, and we've seem to have misplaced our notebook that we've been using for this class, but today, look over there and make sure you're right. Today, it's really important that we have lines to illustrate this synthetic division. What I do is I make a little hook. Notice I'm skipping a line here. I have a reason for doing that. And I ask myself, what number makes this thing equal 0? What number would make the divisor equal 0? It should be obvious. 1. You see a -1 there? The k value is the number that is exactly the opposite of what you see. So I'm going to say k equals +1. K equals, this is really a lousy example because of that 1. And then you see that space I have here? I'm going to start off, make sure your dividend is in descending order based on powers. Biggest exponent to no exponent. And so I'm going to put some little column headings. We have x to the 4th, x cubed, x squared, x, and finally my constant. I'll put a C for constant. And then I start going through writing the coefficients. That first one, 5.
The coefficients are the numbers in front of the x's.
And then what would the coefficient on this x cubed be here? I don't see a number. 1, right. And then -3. Be sure to take the signs. -6. And what do I have here as my constant? Okay, -8. Skip a line.
This is going to take 4 lines total.
Okay. The first thing you do, you take that leading coefficient 5, you carry it down. Then I go 5 times the k value. That's why I'm saying this isn't that great an example, but it's what we're stuck with. So it's a 1. 5 times 1 is a +5. 1 plus 5 is a +6. Then you repeat the process. 6 times 1 is a +6. -3 plus 6 gives me +3. I
It'll
agree.
be clear why he's writing the plus in front of the 6 and the 3 in a moment. Okay, so just bear with them.
+3 times +1 is another +3. -6 plus 3, I agree, but -3. Now, you see why I said it's better when this number isn't a 1, because 1 times anything just stays anything. 1 times -3 is a -3.
So you're always multiplying 5, like, so you do 5 times 1 and then that's 5, and then you do 5 times 1 is 5.
Okay.
Kind of carry it.
And what are we going to have here?
That's right.
I'm catching up.
No, wait a minute. It's -8 minus 3. I think it is -11. Be careful. Now stop and think. You're taking an x to the 4th.
Well, wait. Give him a moment.
Okay, let me give you a moment.
Okay, go back through it. 5 times 1 is positive 5.
5 times 1 is positive 5. 1 plus 5 is 6. 6 times 1 is positive 6. -3 plus 6 gives us a positive 3. Repeat multiplying, and so forth.
This is one of those things, just looking at the finished picture. Yeah, but if I just looked at this, not knowing how to do it, would that help me, I wonder? I mean, where are these numbers coming from? I might be tempted to think you should fill in that line right there, the +5, +6, +3, and then this be the last line you fill in, but no.
Okay, now we have x to the 4th, and we're dividing it by x. Okay, x to the 4th over x. We can cancel an x above and below, and what will we have left? If we cancel, we'd have an x cubed. The variable part, the leading variable part, is x cubed. With this last row is going to be the quotient. That variable power you start with will always be 1 less than the power you started with in the dividend. That variable x to the 4th divided by x says you have an x cubed remaining. So then start decreasing powers. X squared, x. That -3 is my constant. This -11 is my remainder. And we will go plus remainder over divisor, x minus 1. Just like we said it right here. Quotient plus remainder over divisor. The remainder was a -11 over x minus 1. Here, let's look back at that picture. Well, let me give you all a chance to write all that down. But let's look back at that picture of long division that we had. Let me get down. Let's look back. Did we get the same thing with a lot less work? 5x cubed plus 6x squared plus 3x minus 3. I think we got exactly the same thing without all of this variable manipulation here. Am I correct? And notice there was no variable manipulation throughout this process, so that's what makes it nice. Any questions there? We need to do one where the k value is something other than 1, because when we multiply, the numbers will start changing more dramatically. And with that in mind, I want to start with number 4 in the homework assignment.
Number 4 is a very good first example.
Okay, let me write it down.
Ooh. Let me see, Control Shift, can I make it a little bit bigger?
I bet you can.
Oh, I made it too big. There.
5x to the 4th minus 14x cubed plus 11x squared minus 9x plus 6 all over x minus 2. Let me make sure I didn't miscopy it, because even a slight miscopying will throw everything off. That's right. Switch over.
Push it up.
realize the denominator, when the division is written as a fraction, so the divisor is the denominator. This is in the form we need. It's a variable plus or minus a number. So this is an acceptable form for synthetic division. What will be my k value? 2, I agree.
When you're finding k, you change the sign on that number there in the bottom.
The number after the x. The number after the x. Technically you're asking yourself, what number makes this thing equal 0? A positive 2. But it'll just be the opposite of the number you see there. So a positive 2. And then we have our let's put in our column headings. We have x to the 4th. And most people don't write the column headings, and I'll stop writing it after a while. But here at the very beginning, I like to write those column headings.
I confess I didn't used to write them, but I like the way you do that.
Oh, Tony, thanks.
I think, oh no, that's right.
And now let's write the coefficients going across. What's going to go here under x to the 4th? 5, I agree. Here, negative 14. Be sure to take that sign. Here, positive 11. Here, and then we to start the process, you always just take the leading coefficient and move it down. If you have a 5x to the 4th over an x, you'd cancel an x, but 5 divided by 1 stays at 5. So that's why you always just bring down the leading coefficient. And now we start multiplying. 5 times 2 is a positive 10. Negative 14 plus 10 gives us a negative 4. We repeat the process. Negative 4 times 2, 11 minus 8 gives me a positive 3, I agree. What's going to go here? Negative 9 plus 6 gives me negative 3 times positive 2 gives me a negative 6. 6 minus 6 is 0. We have a remainder of 0. That last number is the remainder. In that first example we did, we had a remainder of negative 11. Here, the remainder is 0. That means that x minus 2 divides evenly into that polynomial. We started with an x to the 4th. We decreased that to an x cubed, x squared, x, and finally no x. Here's my quotient.
Do y'all see the pattern here? I mean, how you carry down of where everything goes. Just looking at the finished product, it's not obvious at all. At least I don't think it is.
Mm-mm.
Okay?
And then you leave the 0 out.
That's right. We're going to type in. Here we go. 5x cubed. Remember, use the hot button, the superscript hot button to get that exponent. Then get out of the exponent, minus 4x squared. Superscript. Get out of the exponent, plus 3x minus 3.
That is?
Mm-hmm.
Oh.
Any questions there?
I forgot to mention this. I said a moment ago it'll be obvious why he's putting the signs, even the pluses there, down here rather than just writing a 3.
Well, because the way I then just stick in the variables, so I don't have to rewrite the final answer with the pluses and minuses.
Yeah, that's why you have you put the positive 6 there.
And the positive 3.
You said 1 plus 5 is a positive 6, and you wrote the positive or the plus sign so that, You just stick in the x. But
That's another one of those
the
things
variables.
that I did that you didn't do.
I didn't
Okay.
do. And when I saw that, oh wow. Students are wrong. I'm not the better teacher. He is. Oh gosh. Anyway, any questions before we do another one?
Number 3.
Yeah. Sort of jumping around just, okay.
Oh, I like this.
Got to
Okay.
type it in. And notice how they're writing the answers here. Just R minus 6. I would have rather them have an equal sign. Remainder equals, but for some reason they don't have the equals.
It's interesting that when it's they're having to be the ones typing it, the programmers, they're taking the easy route, R negative 6, rather than typing in plus remainder over divisor. It's sort of interesting, but anyway, here goes. 4c cubed
Plus 16c squared plus 9c minus 15 divided by
they're using that little division
c plus 3.
Okay, switch over. Notice instead of using a fraction bar, they're using the little dash with dots above and below to indicate division. Well, look at the divisor. Is that in the acceptable form? Variable plus or minus a number? Okay, what's our k value? Okay, it's exactly the opposite of what you see there. I agree with negative 3. And then I'm going to put my column headings. I have, well, the largest exponent is a c cubed, c squared, c,
Oh no.
oh no. And I'll put a
What's CON for constant?
CON for constant. Yeah. Now help me fill in this row right here. Here, 4, the coefficient of c cubed is 4. Here,
16, positive,
here,
positive 9,
and
negative 15.
Mm-hmm.
then I skip a line. How do I get this process started? What do I do first? Bring down the 4. You bring down the 4, and then you go 4 times negative 3. That's a negative 12. 16 minus 12 gives me 4 times negative 3 again gives me
Negative 12.
9 minus 12 gives me negative 3 times negative 3 gives me a positive 9. Negative 15 plus 9 gives me a negative 6. What's going to be the variable? First of all, do I have a remainder? Yeah, I have a negative 6 as the remainder. What's going to be the variable part, the leading variable part for my quotient? Right. We start, the dividend had a c cubed divided by c, so we have a c squared, a c, no constant, no variable, plus remainder over, oh, wait a minute.
They write R equal.
Okay, you're right. They're writing R negative 6.
Yeah. I don't know.
A, B, C, or D? Which one?
Oh, they all look alike, don't
Four-
they? You gotta
yeah.
look really close.
4c squared plus 4c minus 3. I think it's B. What do y'all think? Is it B?
The remainder is negative 6. So it's definitely not C, because that is remainder positive 6, right? Is this it? B?
Mm-hmm.
How do A and B differ? Oh, the 3 positive versus negative.
I think it's B.
How do B and D differ? Okay, this 4 here is negative. Oh, wow, you got to look really close.
Where's the all
The
R
remainder.
remainder.
Instead of writing the the remainder over divisor, they're just taking the easy way out at r negative 6.
Yeah, I guess it could
I could write it as 4c squared plus 4c minus 3 r. I would have rather they say r equals negative 6, but they didn't. Any questions there? Okay. There's something called the remainder theorem. And this remainder theorem was very important before modern computers. Oh, goodness. I thought I was misspelling theorem. It looked funny. If a polynomial function
all of these functions we're working with here are polynomials.
That means there are no variables under square roots. There are no variables under in denominators. The exponents are non-negative integers. If a polynomial function p of x is divided by x minus k, then the remainder is exactly p of k.
What the heck is that saying?
That's a good question. How about I'm gonna write this thing here. No, I think I'll do I guess I'll do this one here.
Wait, no. You're going to which one are you working with? 3?
Yeah, I thought so.
Oh, okay.
Okay, I think I'll work with the number 3. Here's a polynomial function. P of x, I don't like those C variables. I think if I ruled the world, one of my first rules would be all variables, all independent variables in algebra problems must be x, and the dependent variable must be y. Okay, but
I think if I were the ruler of the world, that would be my first rule too.
And so I'm going to change those c's to x's. Here's the function: 4x cubed plus 16x squared plus 9x minus 15.
Suppose we had that function,
and
we were told find
p of negative 3. Find p of negative 3. We know function notation. That's saying go to the function, and wherever you see an x, plug in what number? Negative 3. So here we go through. Have y'all ever thought about what it had to be like before handheld calculators? Something just very insignificant could be very time consuming.
Could y'all do this easily or quickly? How long would it take you without a calculator?
Negative 3 cubed is a negative 27 times 4. That'd be a negative what?
108?
Yeah, 108. And then that would be a 9. 16 times 9. 16 times, is that a 144? So a plus 144 and a minus 27 minus 15. Well, fortunately, we don't have to do it by hand. We can punch it into our calculator. Is that what you're doing, Tony?
Yes.
Okay.
I'm plugging negative 3 in for x on this calculator. I'm hoping, but this calculator needs to be a little bit bigger.
Yeah.
They keep deleting it from this computer.
They keep deleting it. Does it require administrative privileges for us to install it on here? They deleted it again. That's why I had to dig up my flash drive.
Look at that.
Negative 6? Wow. A moment ago, we were looking at the same function, and we saw negative 6. Where was that? Wasn't that
Yeah, right there.
oh, there it is, the remainder. That's what the remainder theorem is saying.
How did you get your calculator to say cubed?
Oh, it's a little caret top symbol. If you want to enter something other than a square,
If you look back in old algebra classes, old algebra textbooks, okay,
this little symbol right here is how
it
you
visible?
put the.
there it is.
So you went. So you would go
Okay.
4
Okay.
parentheses. Oh, you can't see. -3. Then the caret top. 3. That's how you would punch in any exponent other than a square.
That's what I use even
been
for a
trying to
square.
figure that out for a
That's what
couple
I
of
use.
months.
Tony uses that little X square key on most calculators. I use a caret top for every exponent. But that's what the remainder theorem's saying. If you need to evaluate a messy polynomial, you have to plug a number in there. You could go through using synthetic division. And synthetic division, suppose you were trying to plug in something like 11 cubed, and you didn't have a calculator. If you look back through old algebra books, you'll see these little synthetic division tableaus popping up everywhere, because every time they got to plug a messy number into a polynomial, they use synthetic division, and the last number is the value of the function.
Like if for some reason in an algebra book, if they needed to plug the number 2 into this top function up here, instead of, without a calculator, they do this. You don't need a calculator with the synthetic division.
Yeah, there's no raising. You don't run into huge numbers or anything. You don't raise things to the 4th power. But doing it by hand, just 2 to the 4th is 16. 16 times 5 is that 80 minus 2 cubed is 8. So, using the remainder theorem to evaluate polynomial functions at numbers really would make it easier if you don't have a calculator. In this day and age, guess what? It's not that significant.
A lot of
imagine.
schools, including Delmar, back in the 90s, said, we can stop covering that in our algebra classes. And then in 2000, what year was it?
2012, the
State of Texas up and announced, wait a minute. Y'all need to be doing that.
Y'all need to teach the remainder theorem. And so, okay, that was fine, Tony. I had never stopped teaching it. But here's the funny thing. The state of Texas listed all the student learning outcomes for every college credit math class, and they put the remainder theorem in there. Why is that relevant today? There's something called the fundamental theorem of algebra. The fundamental theorem of algebra. That sounds important. Surely it's supposed to be taught in some algebra class, right? Not mentioned anywhere in those student learning outcomes.
Now let's do number 5.
Let's do number 5.
They want to get out of here.
Oh, I could just talk and talk.
I know. Okay, it says use the remainder theorem and synthetic division to find f of k. So there's nothing that stops you from just plugging -3 in for x. If that's what you want to do with your calculator, great. But I think you appreciate the remainder theorem more in synthetic division if you see it's easy to do synthetic division without a calculator. So,
yeah, let's do that. Let's
so
do
just like
synthetic
the
division.
great state of Texas to make sure you teach cursive writing, they're making sure we're teaching this remainder theorem.
I
I
didn't
never
realize
that whenever I talk about the great state of Texas, and I never noticed that. I'd always mention the great state of Texas at home and stuff, and my nephew one day mentioned it. Why do you always say the great state of Texas?
a friend of ours was in several Miss Texas pageants when we were very young.
And she'd be there practicing.
The great state of Texas.
Every answer, she'd rehearse her stuff, and she'd talk about the great state of Texas.
Okay, but y'all do understand, you could just take -3 and plug it in there for every x. And use your calculator. You do it like that. You do that, okay? And let's see if it's the same thing as what I get here with synthetic division.
I'm not showing your little thing. There.
Yeah, okay. So I have -2 here under x squared Oh, I wrote my column headings, x cubed, x squared, x, and then no x. And then here I have the coefficient of x cubed is -2, the coefficient of x squared is -10, the coefficient of x is
-12.
-12. Somehow or another everyone lost interest, I think. Here,
No,
what am
they're
I going to
ahead of you,
write?
Tim. You're talking.
Oh,
Yep.
okay. What goes here?
Have y'all caught up? Oh, maybe they're trying to catch us.
Oh, there. Okay. Okay, so how do I get the process started? I got my column headings all put in there. Bring down the -2 times -3 gives me a +6. -10 plus 6 gives me a -4 times -3 gives me a +12. -12 plus 12 gives me a 0. I'll put a +0 just because I need a sign there, I guess. 0 times -3 gives me a -3 plus 0 gives me a -3. Well, that's not a very interesting problem. If we plug -3 in for every one of those x's and simplify, what will we get? -3.
And I'm going to.
Did you agree?
That's what I got.
You punched it in and got -3.
I forgot you were doing it. Okay.
Well, still, everyone can't see her calculator, so.
I mean, you could put it up
Oh, Tim, grab it and show it.
there.
Okay.
And you don't have to type it on.
Yeah. Let's see. We're not making this
That's
up,
cool.
you
So
see.
there's 2 different ways to do it.
Okay.
Mhm.
There it is, punching it in. You got -3, so. And just between you and me, that's what I would do if I needed to evaluate a polynomial
But
function.
if you didn't have a calculator, well, actually, that's not true. Well, if the number were k were -13 and you didn't have a calculator,
Then I would do this. If I had a calculator and I was trying to plug in some weird number, say -17, who wants to write -17 times -17 times
that's something you
-17?
can't do in your head.
Yeah, so.
Or
Okay.
at least I can't do it in my head, and he can. I wonder. Sometimes. Now, what was the answer here? Oh, this is a bad example.
That's what I said.
Yeah, because
Tony.
it's not really. When looking at this, you're thinking, oh well, it's just whatever number's in the parentheses. That's the answer. No, it isn't.
That only
Uh-huh.
works for like those kind of problems, not the ones with division, right?
I'm not sure I understand your question.
Well, because I'm looking at problem number 3, and it's pretty similar to how you guys just solved number 5, but I did it a little different.
Oh, but
No,
number
but
three
three-
is the whole division problem.
Problem.
You're not just looking at what it doesn't just what that last number.
All they want here on number 5 is f of -3 equals -3. That's all they're looking for on number 5 is that last number, the actual remainder. The others are asking
want
you to
you to-
find the
You have to find
quotient.
the quotient, all of that. It's just
That makes sense.
it's a difference in instructions. 1, 2, 3, 4 say divide. Number 5 says remainder theorem. Number 6, do we have time to do this one? Remainder theorem. Imagine plugging a 5 in for x without a calculator. Okay, with a calculator it'll be easy to do. Should we do this one with synthetic division, Tim? Do we have time?
We do, because I'm just going to start. Let's see. I'm going to write it down. I ain't going to talk a lot. Let me write the problem down. Is it a 3x cubed
Cube plus 2x squared
plus 2x squared?
minus 91x plus 30.
And we
K
want.
equals 5.
Okay. So, switch over.
Oh, wait, no, this isn't like, Tim, I'm sorry. This
Oh,
is,
wait
I'm
a
here
minute.
lecturing you about the instructions saying the remainder theorem. Number 5 isn't a remainder theorem problem.
We need
Okay?
to do some. We need to
Yeah.
talk some, don't
Yeah.
we? Mm-hmm.
Okay.
Well, I don't want to. I think I'm going to.
Move over there. Okay, we're not ready to do number 6.
We're not ready to do number 6. I'll go back to that in a moment.
I can't believe I told you. You're doing this because it says use remainder theorem. Here, number 6 says, and it's not the same thing. Does it say anything about using the remainder theorem? Heck, in fact, it doesn't even say divide. This is something new. Okay? So, I'm going to bring this sheet of paper over here.
Mm-hmm.
You can start talking.
Okay, definition.
It's going to define.
Definition. K is a 0, in parentheses. When we were going to school, not we, me and you, but me and my brother, they didn't use that terminology 0 much. They used the word root. And occasionally I still switch back to that. But somewhere along the way in the 90s...
I think because it confused students, they were thinking
square roots
and
cube roots. And there really wasn't a good name for it, root. I think 0 is a much better name for this thing. K is a 0 of the polynomial function p of x if p of k is equal to 0. So if you can plug the number in and it makes the function equal 0, then you say that number is a 0.
And we also know that p of k can also be found as the remainder, so I would say equals remainder.
Mm-hmm. You're right, that's good thinking. If you used remainder of the synthetic division, then the remainder would be 0. Because remember, p of k is given by the remainder. So looking at number 4, I claim 2 is a 0. 2 is a 0 because if we plug 2 in, what would we get? That remainder is 0. So 2, in example 4, 2 is a 0 of the polynomial function 5x to the 4th minus 14x cubed, blah, blah, blah. Is negative 3 a 0? What do y'all think? No, it's not a 0 because you had a remainder of negative 6. Let's go back over here to this one. Was 1 a 0? No, we had a remainder of negative 11, okay? So, now this is important. The factor theorem. If k is a 0 of the polynomial function p of x, I'm using a p of x rather than an f of x. I could just use an f of x, but I'm using a p of x, p for polynomial. If k is a 0, then x minus k is a factor. If k is a 0, k is a number you can plug in and make the function equal 0, then x minus k is a factor. What we're going to do, we're working towards a way of factoring things, polynomial functions, that can't just be factored by traditional trial and error or reverse FOIL.
We've only factored quadratic polynomials.
Suppose we wanted to factor something with a cube.
X cubed. How do you factor it? Turns out to be not that bad, as long as you know synthetic division.
But remember something. The k value is exactly the opposite of what you see in the divisor or the factor. The k value is a positive 2. The factor would be x minus 2. The k value here is a negative 3. The factor has a plus 3. So what the factor theorem is trying to say is whatever the 0 is, the factor is the exact variable and then the opposite of k. And with that in mind, let's go back to that number 6 that I so haphazardly wrote down, thinking that we were using the remainder theorem.
Let's read the instructions for number 6 once more.
Factor f of x into linear factors given that k is a 0 of f of x. If you know a 0, if you know a number, that's saying that if I took 5 and plugged it in everywhere there was an x, what would all this stuff equal? K is a 0, so what would I get if I plugged all the 5 in there? 0, okay? If I use synthetic division, what will the remainder be? 0, I agree. So our K value is 5.
So the significant thing is he's showing you now how to factor something that has an x cubed. If you look at the stuff we've done this semester,
They've been quadratic, 3 terms. It looked like that.
Would it be a negative 5?
No,
No.
they're telling us the K value. They're not giving us the when we're ready to start factoring, the factor is going to be, Mary May, did y'all hear what Mary May said? She's jumping ahead to the factor, and I think it might be a good idea for us to write that down right now. When we start factoring this thing at the end, the first factor we're going to use is going to be variable, and we see the K value is a positive 5, so we need a minus 5. So we already know one of the factors. If we're trying to factor that, one of the factors is going to be x minus 5.
this is the first time we factored something that has an x cubed in it. Normally it has an x squared, it's quadratic, and our factored answer has 2 sets of parentheses.
Here
This
we're factoring
time we're going to have
3
sets of parentheses. In order to factor that x cubed term, we're going to have 3 sets of parentheses in our answer. There's the first set, the one you just wrote, the x minus 5.
There'll be 2 more sets that we're going to have to find. So I'd set my x cube,
And
x squared, x constant, and have my coefficient 3 here, 2 here, negative 91, I agree, and my constant, so 30. They told us k equals 5 is a 0, so I know what this last number right here has to be. The remainder must be,
what should it be?
k equals 5 is a 0, so the remainder should be 0. If I don't get a 0 down here, then I've done something wrong. Let's see. We bring down the 3. 3 times 5 is a positive 15. 2 plus 15 gives me a positive 17. 17 times 5, is that a positive 85? Negative 91 plus 85, is that a negative 6? Negative 6 times positive 5 gives me a negative 30. What are we about to get here? Sure enough, we got a 0. We knew we were going to get a 0 because k equals 5 was a 0. What variable part am I going to have here beside 3?
X2.
Okay, remember the quotient has a power 1 less than the original leading power. So x cubed,
Yeah.
the quotient starts with an x squared, an x, and a constant.
You were right.
I just say it.
Mhm. Well, so at this point, our function f of x, we've already got it factored. Factoring just means write it as a product. And we have it as a product. We could say it's x minus 5, the factor that's associated with the 0, x minus 5 times the quotient. The thing we just found, 3x squared plus 17x minus 6.
But that's really not our answer, because look at the question. It says to factor into linear factors.
Can a linear equation have an x squared? If it's x squared, that's quadratic. We're not finished yet. We now have to factor 3x squared plus 17x minus 6. Well, we don't have to use synthetic division. We know how to factor quadratics like this. We write our 2 sets of parentheses. You're going to have to remember what you know about factoring. It couldn't have been 1 for that last sign was a plus. Last sign's a minus, so what do we know? And now we're going to have a plus and a minus, okay? Hey, well, 3x squared isn't bad.
3x and x.
3x times 1x. Now for 6, what times what equals 6? Well, it can be a 1 times 6 or a... And...
Oh, look at that middle number.
Hey, remember my little rule? 17. If we multiply these two numbers, 3 times 6, that's 18. That number's, I always say if...
Yeah.
Yes, I agree, okay? I think 6 and 1 are going to do it because generally, if this number here is 1 away from the product of the outer and the inner, try the pair that's closest together. If that weren't a 17, say if that were a 10 or something, I'd try the 2 and 3, okay? But since that number is so close to that product there, I'm going to try 6 and 1. Could I put a 6 here? Because then 3 and 6 are both divisible by 3. So we put the 1 there and the 6 there. Okay, now, wait a minute. Now, what we said that was going to be one of each sign, so what do you say is going to go here? A negative and a positive. Let's check. Let's check the outer and the inner. The outer product, 3x times 6, that's an 18x. Negative 1 times x, that's a minus 1x. 18 minus 1 gives me a positive 17x. Is that what I needed? It sure is. Look at that. This is the first time we factored a cubic. We factored a cubic into 3 linear factors.
This is a huge step in algebra. You might say, well, wait a minute. How the heck would you do it if you don't know that k equals 5?
I was going to try to get them to figure out. There's one drawback to this factoring method. You got to know a 0. You have to know a number that can be plugged into the function to make it equal 0.
But it's not really, there's a way, you'll see how to find those in a little bit.
Yeah, we'll see how to find them in a little bit.
Give a little.
Tony has a little recipe, and you know something? I like it. I like his little recipe, okay? How to factor a polynomial. Maybe we should type in this answer first.
Oh, yeah. Oh, gosh. I hope we haven't been talking so long that...
Make time to say.
Oh, so it was x minus 5.
Just like when factoring a trinomial, the order doesn't matter. I put the 3x minus 1 before the x plus 6. I could have put the x plus 6 and then the 3x minus 1. I could put the x minus 5 at the end. As long as you have the exact same stuff inside the 3 sets of parentheses, the order in which you type those parentheses does not matter.
And theoretically, you could get this with trial and error. Could you imagine writing out 3 sets of parentheses and then trying to arrange
3x cubed. Well, we'll have a 3x on one and an x and an x on the other. It would become a nightmare.
And then 30, you would need 3 numbers that multiplied together to give a positive 30.
Well, negative 5 times negative 1 times positive 6. Yeah, that gives you a positive 30, but it would be a nightmare.
Okay, I mean, if
going about that.
Like this one. Can you imagine writing out 3 sets of parentheses? The first, so it's going to have to be a 2x and then xx. And for 15, it's either 1, 1, 15 or 1, 3, 5.
Mm-hmm.
Is that it?
Yeah.
But how do you arrange them so you get that? Well, Tim, go ahead and write out our sequence of steps.
I'm going to look at what you have written there, okay? This is one of those things that I would never do, okay? But I see that there's that's a good idea.
This is how to write out, or how to do problem 6, 7, 8.
How to factor a polynomial when a 0k is given. That is CE, and that's it, when a 0 is given. When they give you that k, the first thing you do, use synthetic division. Move it up some. Move it up. First thing, use synthetic division.
So These are the 3 steps you'll use on problems 6, 7, and 8.
And then we automatically know one factor, x minus k. It's just x and exactly the opposite of the k values. Here the k value was a 5, and so it became minus 5. If that k value were a negative 3, it'd be x plus 3. So I'll say x minus k is a factor.
I usually write that one first, but you sure don't have to.
And what do we do after we did that? Okay, once we use synthetic division, and we had a quadratic expression remaining, and so we factor the remaining quadratic expression by trial and error. Factor the quotient using trial and error.
So the final answer will have 3 sets of parentheses. Write it out.
Yeah, final answer. And the first factor that I'll write down will be that x minus k. X, and then just the opposite of whatever the k value was.
And the other two are the
Things that we got by trial and error. I'm going to write right there. Trial and error.
I like it when I compliment you, Tim. It just means, okay, someone that has a few degrees in math really understands what you're saying. That's good, Tim.
Yeah. What you should understand. The question is, can we get the people that don't have the degrees in math to understand?
Oh, that's another question. Are we ready to try number 7? Okay.
You know, I remember when we had to start back doing all of this, the great state of Texas said we had to cover it. And in a plain college algebra class, it was so difficult getting all of this done in, one class session. But now that we have this combined 2 class time, now I have to worry about racing through it. I really enjoy this stuff.
And like the synthetic division is really foundations.
Oh, yeah.
But, so what? We just mix it all together. There it is.
So we want a factor. F of x equals 2x cubed. Okay.
Minus 5x squared minus 28x plus 15.
X plus 15. And they tell us what's the 0?
Negative 3 is a 0. But notice it doesn't say k equals. You've just got to know that negative 3 is your k.
Yes. K equals negative 3 is a 0. I'll write it out there.
So you're going to start off with your synthetic division, Tim?
I sure am, Tony. That's what I just wrote your little recipe out. Use synthetic division. That's the first thing we do here when we're trying to factor a polynomial like this. So, okay, there's my negative 3. We have x cubed. Let me put in my column headings. X cubed, x squared, x, and a constant. What's going to go right here? Here. Okay, here. Here. I agree. Now I'm going to skip a line. Oh, bring down, not the negative 3. Oh, bring down the 2, right? And then 2 Okay, 2 times negative 3 is negative 6. Negative 5 minus 6, I agree with negative 11 here. Okay, negative 3 times negative 11, that's a positive 33. Negative 28 plus 33 gives me I think it's a positive 5. You're getting ahead of it. Negative 28 plus 33 gives us a positive 5. And then you go positive 5 times negative 3. That's where the 15 comes in. And that's not a surprise. That's not surprising. It has to be a 0 because they tell us that negative 3 is a 0. To use this factoring process, you have to know a 0. So, variable part here. Good. And an x. So, we're trying to factor f of x. That means write it as parentheses. Write it as a product. We just did, where's my little sequence of steps, your little recipe? Let's see, here it is. We use synthetic division. That was step 1. Now, x minus k is a factor. So, x minus k, that's the first thing. Okay, good. It's x, and it's exactly the opposite of the k value, so that minus 3 becomes a plus 3. And this is really the division algorithm that I'm using here. Divisor times quotient will give us back the dividend. If you remember that division algorithm when you were learning long division back in elementary school.
I'm sure they remember that. I suspect the elementary school teacher didn't even mention the division algorithm.
You think? Now
I
we
think
need
they
to
told him how to check it.
Okay, now we got to factor this thing here. So I'll go ahead and bring down the x plus 3. We have our 2 sets of parentheses. What times what is going to give us a 2x squared? 2x and x, okay. I like the signs. What do I know about the signs? Okay, the last sign's a plus. So you have 2 of those first signs. I agree. Negative and a negative. Okay, so where are we going to put the 5? The only possibility for 5 is 1 times 5. So I agree. Put the 5 there, the 1 there. Let's check. The outer product is 2x times a negative 5 is negative 10x. Negative 1 times x is a negative 1x. Negative 10 minus 1 is negative 11x. Is that what we needed? Yes, it is. You have to remember how to factor quadratics by trial and error to be able to factor higher order polynomials. We know negative 3 is a 0. There are 2 other zeros. What other numbers could we plug in up here and make this function equal 0? Once it's factored, it's pretty easy. When would this factor be 0? What x value? 5. When is 2x minus 1 equal to 0?
I'll give you a hint. It's a fraction. You set 2x minus 1 to 0 and solve for x, isolate the x, what would you get?
1/2. Okay, so we now know if they had asked us, once it's factored, what are the zeros? Well, we have them right here. Set each factor equal to 0 to get negative 3, we already knew that, positive 1/2, and positive 5. Once the polynomial is in factored form, finding the remaining zeros are easy.
In fact, if your polynomial has an exponent of 3, if that's the biggest exponent,
You cannot have more than 3 zeros.
in general, there's 3 zeros.
Yes.
I have no idea how you thought those numbers
Oh, yes, you do.
I like that.
If I wanted to set the, well, first of all, did you type in the answer?
No.
Okay, go ahead and type in the answer.
The first one was x plus 3. And
I know how you
then
got that.
A 2x minus 1
Uh-huh. we would just see.
and x minus 5.
Okay. Any questions just on this?
Okay.
Okay. So
Now-
a little extra here.
I have a question. When does, suppose we wanted to know, when does 2x cubed minus 5x squared minus 28 plus 15 equal 0?
How would you solve that?
We've already got it factored. We have it factored right here. It factors as x plus 3 times 2x minus 1 times x minus 5. So we'd set that product equal to 0. We know from the zero factor property that the only way a product can be 0 is for one or more of the factors to be 0. That means either x plus 3 is 0, 2x minus 1 is 0, or x minus 5 is equal to 0. Solving the first one, move that 3 over to give us x equals. Well, we knew that negative 3 would be a solution because they told us that if you plug negative 3 in, it's going to make it equal 0 by saying negative 3 is a 0.
What are the other two zeros?
See, I felt that. I felt that. Yeah.
Okay.
I just, how did you guys do something else?
2x, that says 2x is equal to positive 1. Divide by 2 to give us x equals. Okay, there's the second 0. What's the last 0?
It's the last zero. It's not a fraction.
Positive
Positive
5.
5.
I just didn't.
I think that's what the great state of Texas wants y'all to be able to do.
I see what you
See how to factor and solve a cubic equation. I think that, I mean, I'm guessing.
And I think that's what's important from all of this stuff that we've been doing today. Suppose you have something like an x if it were an x to the fourth, what you could do is, okay, use a 0 in synthetic division to break it down. Well, you'll still have an x cubed remaining, so
Do
then you got to
synthetic
find
division.
another 0. Do synthetic division again. Even if that were 2x to the 10th. As long as you have a 0, you can start going through, breaking it down, finding zeros as you go, and get it in factored form if it's factorable.
Let's do another example of this faction.
There's one thing I want to mention. Think about solving a quadratic equation. A quadratic equation, what variable, what's the biggest exponent on the variable? If it's x squared, and most of the time we had 2 solutions, correct?
With the quadratic formula, the answer would be negative 3 plus minus square root of 17 over 2. That plus minus is 2 different numbers.
Okay. X cubed, how many solutions when we found the zeros, how many did we get? 3. In general, the number of zeros of a polynomial function can't exceed the the largest exponent. That thing right there of 3, I know there can't be more than 3 zeros. So once I found the 3 zeros, that's it. I don't have to keep looking for other numbers to plug in to make it equal 0. The fundamental theorem of algebra says the number of zeros cannot exceed the largest exponent.
So if it's like x to the fourth, x to the fifth, that would be 5, so it's factors.
Yes, that is correct. And that means if it were an x to the fourth, you couldn't have more than 4 zeros. You have the 4 sets of parentheses. You could set each one equal to 0. Or if it were an x to the fifth, you couldn't have more than 5 sets of parentheses and 5 zeros. Okay. Number 8. Let me write it down. Okay, here's the thing we want to factor. factor f of x equals 2x cubed plus 5x squared minus, is that 102? 102x, okay, plus 135. And they tell us that negative 9 is a 0. And since negative 9 is the 0, we know that's going to be our k value. K is equal to negative 9. Okay. So we'll set it up using synthetic division. K equals negative 9. My largest variable in the dividend, the thing being divided, is an x cubed, x squared, x constant. Oh, I'm getting tired of talking, so y'all call out this line here. What goes under x cubed?
2.
I agree with 2.
5.
5. Negative 1 or 2.
And, okay. Bring down the 2, okay. Here, negative 9 times 2, I agree, that's a negative 18. Here, five minus 18 is negative 13. Okay, negative 13 times a negative 9, is that a
90
117?
Yeah.
Is that a positive 117? Negative 102 plus 117, I'm getting a positive 15. Positive 15 times a negative 9, is that a negative 135?
It's a 90 plus 45, yeah.
It better, I know it's a negative 135 because I know what this number has to be here. What is it? What is this number? It has to be a 0, so that better be a negative 135.
You do x squared.
Okay, so it's 1 less than that biggest power. I agree. X squared, x, and my constant. Okay, oh, good. The vocal minority has got the hang of this, I can say. It's going to be x. Oh, yeah, good thinking. Red. That's going to be x. The k value was a minus 9, so I have a. Good. So, there's the divisor times the quotient. 2x squared minus 13x plus 15. Oh, good. But I mean, we're getting another break. That last sign's a plus, so we're going to have 2 negatives. I agree. So, parentheses and parentheses. Okay, so for 2x squared, you said what? 1x times 2x? And you say a 5 in it. It's either 1 times 15 or 3 times 5. It's not going to be a 1 and 15. That just get us too far away from 13. So stop and think.
5 and 2 is 10.
Okay, so you're putting the 5 here and the 3 there. And if we check the outer product, and once again, we were just playing, Mary May, were you just foiling in your head, seeing? Okay, you see, that's what you're doing. You're going through. This is what we're thinking in our head. The outer product, x times negative 3 is a negative 3x. And then the inner product, negative 5 times 2x is a negative 10x. Negative 3 minus 10, that's a negative 13x. Is that what we wanted? Yes, it is. And once again, you could type the x minus 5 first if you wanted to.
Okay.
Just put in parentheses. You can put, the order doesn't matter as long as you have the exact same 3 sets of parentheses. The order doesn't
You
matter.
can't have a 2x plus 3. No. It's got to be a 2x minus 3. And you can't have an x minus 9. It better be an x plus 9. So the natural question is, how the heck do we find these zeros?
If they just gave you this thing here. Oh, by the way, it's an easy task. If they said, okay, what are the other zeros? You know one of them, x plus 9 is equal to 0 when x equals
Negative 9.
negative 9. What about this one? When would x minus 5? When is 2x minus 3 equal to 0? Move the 3 over, divide by 2, and get 3 over 2. So we can, once it's in factored form, we can find the remaining zeros easily.
And that's the K.
Yeah, those are the 3 K's.
K's.
Those
Now,
are the 3 K's.
Let me ask you something. Do you think I could plug in 11 here, here, and here, and it all equals 0? Are there any other numbers other than negative 9, positive 5, and positive 3 halves? Are there any other numbers you could plug in and make that equal 0? No.
All the billions of numbers
There are
out
billions of numbers, uncountably infinite many numbers out there. Here are the only 3 numbers in the world that can make that thing equal 0. So if you were just given that and they said, okay, find a number that'll make it equal 0. Well, where do you start? What would you plug in? How would you figure out a number, a 0? We have something called the rational zeros theorem. I was going to say rational root test. It's that old terminology that we use.
Now that I've accepted it, I like that terminology zero.
I liked it immediately. It's just
root.
There's
no cube. We're not doing anything with square roots here. So
because
calling those zeros roots back in the olden days was not a good thing.
I don't think it was a good term either, Tony. Oh, I should make a note. There, it's easy to find the zeros then. Okay? Rational zeros theorem.
Rational is another word for any number that can be written as a fraction.
Oh,
that includes the integers, because you could always make 9 and 5 into a fraction by putting them over 1, and the real fraction.
But remember, something like the square root of 2, that's irrational, okay? That's not rational. But when you're solving by factoring, are you picking up square roots along the way? If you're factoring, do you expect that to have a x plus the square root of 7 or x minus the square root of 5? No. And so you're not going to be finding irrational roots anyway. And so having the restriction of it being for rational zeros, that's not a hardship, okay? Possible rational zeros of the polynomial function p of x I should have just said possible rational zeros of p of x must be in the form it's a fraction. We have to take into account sign changes, and to do that we just have a positive or negative. So it can be a plus or minus. The number on top must be a factor of the constant term. Factor of constant term. That's the thing in the problem that doesn't have a variable attached to it.
Now, don't be panicking. You've made it through the hard part of this.
You made it through the hard part. This isn't bad at all. The denominator For it to be a possible rational zero, the denominator must be a factor of the leading coefficient.
Constant term is the last number. The leading coefficient is the first number. Like on number 8, 135 is the constant.
The leading coefficient is 2.
And it would look better to me.
What this is going to do, I'm going to extend it. Now, there. Realize what this thing does. This rational zeros theorem gives us a finite list of numbers that could possibly be zeros. Out of the infinitely many numbers in the world, this little list will give you about maybe 20 numbers that could make the function equal 0. And so if you didn't know a 0, you could apply this test and you get about 20 numbers. Okay, take the first one, plug it in. Does it equal 0?
Or do synthetic division.
Or do synthetic division. You just go through the list until you find a 0. And as soon as you find a 0, you can use synthetic division to start breaking it down. To illustrate, I don't want to do number 8, okay?
Number 8.
I mean, I don't want to go through all the possible rational zeros because I don't want to have to write out the factors of 135.
Number 9?
Oh, well, okay, here's one.
What's that?
Oh, I forgot. This is good. Okay. They're all multiple choice. I'm going to need a whole page for this stuff. Isn't that what you want to hear your teacher say? Oh, I need a whole page for this. Here's the function. 2x cubed plus 6x squared plus 14x minus 8.
If it said, if you were going to try to find all the zeros, and they don't give you one, they don't say k equals, well,
how would you even know where to start? Well, maybe 5 would make it equal 0. Maybe -7. This rational zeros theorem gives us a finite list of numbers that could possibly make the function equal 0. Realize it's going to be positive or negative. It's going to be a big fraction. And by the way, I don't have to worry about that -8. I don't have to say, the factors of -8 or 1 times -8 or -1 times +8. We're going to take care of all the sign changes. That's the purpose of this plus minus. All we need on top are the factors of 8. Factors of the constant term, 8. On the bottom, we're going to need the factors of the leading coefficient. Oh, that's 2. That's nice, because there's only 2 positive integer factors. Let's write out all the factors of 8.
What numbers multiply together to give 8?
4 and 2.
Okay, 4 and 2 and?
8 and 1.
Okay, I think I'm going to write them in numerical order. It's 1 and 8. 2 and 4. What about the factors of 2?
2 and 1.
Yeah.
Okay, I'm going to write them in numerical order again. 1 and 2.
Does it matter when you type it out?
No.
No.
Just for
And these are all multiple choice problems, so it's not bad at all entering in the answers. You need an organized way to take every one of these numbers on top, put it over the first one. Then take every one of those numbers there, put it over the second one. And so what I'll do, there's 1, 2, 4, and 8. 1, 2, 4, and 8. I'm going to put all of those numbers over 1. And then I'm going to take 1, 2, 4, and 8 and put all of those numbers over 2. I agree. So we'll clean it all up in a minute. Put them all over 2. There are all the possible numbers that have a chance of being zeros. Now, of course, we know in reality there could be no more than how many zeros? 3, okay, but this is going to be more than 3. It's just the numbers that could possibly be 0. Let's start simplifying them. Let's clean them up, as I say. 1 over 1 is 1. So plus or minus 1. There's one of the solutions. 2 over 1 is 2. 4 over 1 is 4. 8 over 1 is 8. You don't have to show the over 1s. And then 1 over 2. That's 1/2. So plus or minus 1/2.
Now, what's about to happen?
2 divided by 2 is? We already have that listed, so we can mark that out. 4 divided by 2. 2, we already have that one listed. 8 divided by 2. 4, we already have that listed. Look at this. Out of infinitely many numbers, there are only 2, 4, 6, 8, 10 numbers that could possibly be zeros. So if you needed to factor this, well, start off with k equals 1, do synthetic division. You get a 0, great, go on and simplify further. If not, go to -1. But these are the only numbers that could possibly be 0. And if you went through the entire list and none of them gave you a remainder of 0, that means the thing is prime. It can't be factored.
So you just have to do it by trial and error?
Yes.
Well, trial and error wouldn't work it there. I mean, you can't do it there.
Do you mean we factor it by trial and error then? Or what?
To use these to do the
Well, you'd have to go, you'd first of all use 1 till you get a 0 for remainder using synthetic division. If you get a 0, that's when you use trial and error, okay? But if you get a -1,
if you don't get a 0.
If you don't get a 0 from +1, do it -1. Just go through the list until you get a remainder of 0 using synthetic division.
And we were so nice. We didn't assign any.
Dr. Kirkendall used to say,
"Oh, just stop right there."
yeah,
And I
we've given you all the pieces you need. If at odds favor, you will never need to take a higher order polynomial, factor it, and find the zeros. I would bet large sums of money that there'll never be a time anyone will come in here and tell you, oh, you got to find the zeros. Here's a polynomial function, find the zeros. I don't know what you're going to do with your life,
put it together,
but I've given you enough so that you can put it all together. You find a finite list, then you start using synthetic division on it. Does it equal 0 here? If so, then start factoring by trial and error. If it's not a 0, then go to -1 and do it. Go to +2 and do it. You just keep on going until you find one that gives you a remainder of 0. And if you make it through the whole list and you don't get a remainder of 0, just bad luck. The thing is prime, it can't be factored.
Okay.
Which means there are no rational zeros.
So which A, B, C, or D am I going to click?
The order doesn't matter as
doesn't
long
matter.
as it has all the numbers. 1, 2, 4, 8.5. Yeah, I agree. When I look at that, you know what I think they're doing? I think they're taking 1, put it over 1, 2. 2, put it over 1, 2. I take all the numbers on top over the first number in the denominator, all the numbers on top over the second number, so that the order isn't exactly the same. But let's do another one. Okay. Okay, number 10.
So, are those 43s going to be used for anything on
Oh,
this
that's
particular
another question.
problem?
Look back at this one here. On number 9, look at my work.
Oh,
Suppose I asked you, find all the zeros of 2x cubed plus 16x, or the possible rational zeros. Suppose instead of a 6, that was a 16, and then suppose instead of that being a 14, it was a 44.
would that
change anything?
No.
No. The only numbers you use for finding possible rational zeros is the constant term and the leading coefficient.
What's your question?
And so if the constant term was a positive, would you switch it to a negative?
No, if it were a positive, though, you could have a positive 1 times a positive 8 or a negative 1 times a negative 8. You don't worry about the signs. That's the beauty of the rational.
Minus in front.
That rational.
I also had a quick question because I misunderstood with the cubed. I thought that you had to have 3 answers or less, but it's 3 answers
That's
or
for-
more.
That's for factoring. That is for factoring and finding the actual zeros. These are not the zeros. These are the possible numbers that could be zeros. If we went through and found the zeros,
It better only be 3.
it'd be 3 from this list right here.
But you're not really finding the zeros.
You're just finding the
the
possible, the numbers that could possibly be zero.
And there were 2, 4, 6, 8, 10 possible there. Now,
Okay, number 10.
number 9.
Well,
Oh, no, we've already done
Done-
that. You're right,
done
number
that.
10.
So P of X, here's the function we want to find the possible rational zeros for. 3x cubed plus 43x squared plus 43x plus 27. And we want to find the possible rational zeros. We need the, I always find, for some reason I find the ones that go on top first. That's just my habit. I do the ones that go on top first, which will be what's going to go on top. Factors of 27. So that's why I do the factors of 27 first. We want the factors of 27.
And factors of 3.
There's certain things that I've just made habits throughout my career, and that's one of them. I always write down the factors of the constant term, and then I write down the factors of the leading coefficient, and this is where you say factors of 3. Okay, so what are the factors of 27? I'll get us started. There's 1 times 27. Well, there's not that many, I guess. 1 times 27. 3 times 9. Is that it? Mm-hmm. Yeah. What about the factors of 3? 1 and 3. So we're going to take every one of those numbers on top, put them over 1. Then take every one of those numbers on top and put them over 3. Okay, good. So 1, 3, 9, and 27. We're going to put them all over 1.
Which is just going to give us 1, 3, 9, and 27. Right?
Mm-hmm. That brings up a good point. You will always have a 1 down here in the denominator. So that means the factors of the constant term will always be possible zeros. And then we take all that 1, 3, 9, and 27 and put them over. And take the 1, 3, 9, 27 and put them over 3. And it's time to start cleaning this up. 1 over 1, 3 over 1, 9 over 1, 27 over 1. Those reduce very nicely just to. So 1 divided by 1 is 1. I don't like that. So 1 divided by 1 is 1. 3 divided by 1 is 3. 9 divided by 1 is 9. 27 divided by 1 is 27.
You got 1/3.
1 divided by 3 is 1/3. We don't already have that. Oh, this one's working out really nice, like number 9. 3 divided by 3 is 1, we already have it listed. 9 divided by 3 is 3, we already have it listed. 27 divided by 3 is 9. Okay. So out of infinitely many numbers, 2, 4, 6, 8, these are the 10 numbers that could possibly make that function equal 0.
How many of these, at most, how many of these could equal 0?
Three. No more than 3 of them could actually make that function equal 0.
Oh, wait. Which is it? Is it D again? Was it D the last time? I don't know. That's it?
Mm-hmm.
Now, let's see. 11 and 12. I wonder which ones we want to do now. Which one do y'all want to see done?
Hey, let's do number 11. Number 11. We'll do number 11.
Smaller.
Yeah.
Same
It's
thing.
another one of the possible rational zeros.
I think starting with number 13, it's review. I don't remember what it is. Maybe
Cut points.
cut point or quadratic formula. Once you start writing it.
Okay. This is number 11. P of x is equal to negative 2x to the 4th plus 2x cubed plus 5x squared plus 18. Okay.
Oh, it's a fog engulf.
Uh-oh, they're
Okay.
trying to get you ready for inverses, which we'll be seeing next time.
Okay, so here, this will be our last example.
Okay, we need the it's plus or minus.
Factors of which number on top?
18.
18,
Okay,
good.
factors of 18.
And factors of 2.
Mm-hmm.
And then on the bottom we have the factors of 2.
Oh,
I forgot the O. There. So let's write out those factors of 18. I think there's more than in the other two problems. You could have a 1 times 18 or
2 and 9.
2 times 9 or 3 times 6. Now the factors of 2, that's easy, just 1 and 2. We're going to have to take all of the purple numbers, put them over 1, then take all of those purple numbers and put them over 2. So,
Maybe you could do the first one without actually
hey,
over 1.
what do y'all think? Y'all let me just drop that over 1 and just write plus minus 1, plus minus 2, plus minus
3
3,
over 1.
6 over 1, 9 over 1, 18 over 1. Okay, then we go the purple 1 divided by the black 2. That's 1/2. Do we have 1/2? No, so we better write it down.
Okay, do y'all see how it's getting this without showing all the steps? Everything up here over 1. That got the first numbers.
And then we're taking every one of them, putting over 2. 1 over 2 is 1/2. What about 2 over 2? 1, we already have it. 3 over 2? I don't think we have it. We better write it down.
And then 9 over 2.
Okay, well the 6 over 2, you're saying that's a 3. So 9 over 2?
Mm-hmm.
What about 18 over 2?
Like we already have 9, right?
We already have it. Realize with the rational zeros theorem, the factors of that constant will always be possible rational zeros.
We have quite a few here. 2, 4, 6, 8, 10, 12, 14, 16, 18. But out of all the billions of numbers, here's the only...
Before 9/11, I remember I would always say, oh, suppose some terrorist group took over this classroom and said, you can't leave here until you find every zero of this. Number 11, what's the maximum number of zeros there could be? 4. Well, here's the possible. You find your possible list.
Start going through.
And start going through
until you find the 4.
And so, yeah, it'd take a while, but you could get it done. Of course, I don't make that little remark anymore. I never talk about the math terrorists taking over the classroom and not letting us leave until...
That's why I failed math like 10, 12 years ago. It's because literally I missed my whole other class because he wouldn't let me leave.
Oh my goodness.
Wow.
Wow.
It was bad. That was like, I'm going to say 13 years ago, but that was in Colorado, and that was at Arapahoe Community College.
So you weren't in the great state of Texas back then.
Not yet.
No.